let's turn our attention now to the idea of concavity and talk about the definition of concavity. So let f be a differentiable, or let f be differentiable on an open interval I. This is an I, not an L. The graph of f is concave up on this interval I if f prime, the first derivative, is increasing on the interval, and it's concave down on I if the first derivative is decreasing on the interval. So let's think about what it means to be increasing and decreasing. If I have a function that looks like this, clearly this is concave up. Now if I think about the slope of the tangent line, the slope here is going to be negative. The slope here is going to be positive. It's moving from negative to positive, so it's increasing. That's what we're saying right here. So the graph of f is concave up if the first derivative is increasing, which is what I'm seeing here. And then just the opposite, something like this would be concave down. And if I think about the slope of the tangent line, this would be positive. This is still positive, but less than the previous. Less. Now we're going negative. So this is a situation where the first derivative, because remember the first derivative will give you the slope of the tangent line at a specific point on the function, it's definitely decreasing. The values are getting smaller and smaller and smaller. And on that case, when it's decreasing, I'm concave down. So what we need is a test for concavity that we can make this determination. And so let's go ahead and just quickly recite this test so that you know what to be looking for. So let f be a function whose second derivative exists on an open interval I. So I know I have the first derivative and the second derivative on the same open interval I. Now remember, the second derivative is a rate of change of the first derivative. That's what derivatives do. The fifth derivative would be the rate of change of the fourth derivative, if they both exist. So if f double prime, the second derivative, is greater than 0, so if the second derivative is positive on this interval I, then f is concave up on that interval I. So if the second derivative is positive, that means the first derivative is increasing. If the second derivative is less than 0, in other words, negative on I, then f is concave down on I. The second derivative being negative means the first derivative is decreasing, which is what we're seeing in this example up here. So let's move on with this idea and talk about the idea of an inflection point. There's a theorem to help you determine the inflection point. And an inflection point, if I have a function that looks like this, clearly I'm concave down and clearly I'm concave up. Somewhere in here, like maybe roughly there, I switch from going concave down to concave up. And that is what the inflection point actually is. So if f of c is a point of inflection on the graph, so this would have coordinates, x would be c, and on the y-axis, obviously, then this would be f of c. So if f of c is a point of inflection on the graph of f, then either the second derivative is equal to 0 or the second derivative d and e doesn't exist. Well, that's the same sort of thing we saw with the first derivative test. When we looked for mins and maxes, we looked for when the first derivative changed signs. So where was it that the first derivative was 0, and then we looked on both sides to see if it went from positive to negative or negative to positive. Well, this is the exact same idea. Only here where the second derivative is 0, or does not exist. And likewise for the first derivative. If the first derivative didn't exist, that was another candidate for a critical value. If we find that point, then what's happening is we're changing, or they're candidates anyway, for a change in inflection. Whereas for the first derivative, those were all candidates for local mins and maxes. There was something changing there. What was changing is in the first derivative test is the slope of the tangent line going from positive to negative or negative to positive. That indicated a local min or max. Here with the second derivative, what we're looking at is there's a change, and the change is from concave down to up or up to down. There's a change in concavity at that inflection point. So that's the basic idea behind concavity, how to determine what the concavity is, and to identify the inflection point where the concavity changes. So now what we need to do is simply take a look at some examples to see how to apply all of this.